Thank you, Billy, for the kind introduction. I also appreciate our soft robotics community. I feel like I look out and I see a lot of really accomplished people, but really kind people as well. So thanks for having me here today. I just started as an assistant professor at BYU this year, so I'm brand new into this professor gig. But I'm really excited today to talk about a little bit of my past work and then some of the future directions that I see that taking as well. So without any further ado, where we're going to end up today is talking about a robot that looks like this. This is a large-scale, untethered soft robot, and it can operate untethered. This is a basketball for scale here, so it's capable of changing its shape to pick up a basketball while operating in an untethered way. And so we have these untethered robots, we have large-scale shape change, and I want to talk a little bit about how these work under the hood. One question that I would like to ask I think we should ask ourselves, we're here talking about shape morphing and morphing robots. I think it's interesting to think about how we represent shape. When we say our robot is changing shape, how do we quantify shape and what do we mean by shape? There's some nice inspiration, I think, from computer science. Typically, shapes are represented with pixels or their 3D equivalent of voxels, where we look at a shape as a collection of individual bits of information. And we've seen that there's been a number of robotic systems that have developed shape-changing capabilities using that type of idea. So we have pin displays or large swarms of robots or robots that are constructing form using kind of individual pixels or individual voxels to create robots or structures of different shape. I think this is a really powerful technique and a useful one in some ways. However, I think there are some limitations of a pixel-based representation of shape. One is that if I want high resolution in one spot of the robot or of the image, I need high resolution everywhere on the image. So if I want fine details in some spot, I need to put a whole bunch of individual shape-changing elements across the body of the robot. Another challenge is that there's often a trade-off between the amount or degree of shape change and the resolution of the shape change. So if I want my robot to be able to stretch really big, I can't have hundreds of little tiny pins that are going to stretch really big in each direction. So I think another interesting representation of shape that we see in computer graphics is the triangle mesh. And this is, of course, going to have some other limitations, but also some other capabilities in that you have potential for adaptive resolution. Where your mesh has low detail, you could have a very sparse mesh. And where you have really high detail, you could have a more dense mesh. And you have the potential for a more expressive system. And there have also been a number of really interesting hardware developments towards building these robotic triangle meshes as well. And I guess just to show a little bit of inspiration, I've been inspired by this work in computer graphics where these authors develop a computational tool that can morph from one mesh to another. And so these two meshes are actually the same graph, the same connections between vertices and edges, but using a computational tool, they're able to smoothly morph between these things. And so at this point, the idea is, well, it'd be great to make a robot that would capture some of those capabilities. And so probably the first idea is let's take the nodes and the edges of our computer mesh, and let's replace the edges with actuators that can extend and contract, and the nodes with joints that connect these adjacent actuators. And indeed, many people have done this types of thing. I've tried to highlight a few of them here, but of course I'm missing some. There have been a number of really interesting shape-changing meshes that have been developed by various researchers since the 90s, over a long course of time, really interesting results. However, I think there's still some challenges that remain. Typically, the expressiveness or the shape changeability of these meshes is limited by the extension ratio of the actuators. And it's very hard to build actuators that are capable of high extension ratio, that aren't brittle, and that work reasonably well. So typically, we're building custom actuators, and they typically are brittle and have other challenges. So since we're at a soft robotics conference, this might seem like an opportunity where soft robotics can contribute the ability to have high extension, as well as the ability to add some natural compliance to the system. And we've heard about some of those ideas this afternoon already. And so one of our key insights was like this. If we take our kind of standard idea of a truss where we have within each actuator, we store all of the material when it's compressed, and then we deploy all of that material. And that means that we have to always have all this kind of extra material stored within the robot. Our idea instead was a little different. Let's take a continuous beam of material and let's bend that beam to form a triangle in a triangle mesh. And then we can change the shape of this triangle not by stretching and retracting an actuator, but by moving the joints along this triangle. So that's the abstract idea. Physically, we're able to realize this system as something that looks like this. So this red portion here with the tiger stripes is an inflated fabric tube. And this is a little cart robot that essentially pinches that tube and drives back and forth along the tube. It allows air to flow from side to side, but what this basically does is it creates a point of low bending stiffness that acts as an effective joint in this continuous beam. And then by driving that joint back and forth, we can change the relative edge lengths of a triangle while maintaining the overall constant perimeter of the triangle. And so when coming up with it, we tried to call this an isoperimetric robot because it's maintaining a constant perimeter across different motions. Its fundamental components are it's made of inflated fabric tubes. It has these robotic roller modules that drive in 1 degree of freedom back and forth along a tube. And they're powered by a standard DC motor. So instead of inflation to actuate this robot, which can have some associated inefficiencies, we're powering this robot directly from an electromechanical system. And then we connect these adjacent roller modules together using spherical joints. And the result is that we're able to create this large scale, approximately human scale robot that is capable of untethered locomotion by changing its shape, by undergoing some pretty dramatic shape change. And we can see here that it, so this is a 1x video, so I would not say that this robot is fast. It's certainly not going to, break any body lengths per second speed records. But I think at this scale, for a largely inflated structure, I think it's interesting that we're able to achieve these types of locomotion speeds. Here's another demonstration of kind of our kinematic model of this robot working alongside the physical robot, showing that we have the kinematics that allow us to describe how this unique kind of triangle mesh with this interesting constraint is capable of going through a number of different shapes. And when we think about the shape change of this robot, if we think about other robots as individual pixels or voxels that are extending and contracting, I almost think of this robot, it almost is changing its shape like a blob of clay. It's like maintaining the same amount of material at all time. The sum of all the edge lengths is always a constant here. But just as I can morph a blob of clay into a number of different shapes, I can kind of morph the structure of this robot into a number of different shapes. And so one question that we've had in completing this work is that we were able to develop this interesting octahedral structure, but what are the other types of shapes that we can enable with this sort of robotic system? And I guess if I was to describe this mathematically, I would say which graphs or which meshes can be decomposed into triangles such that each edge in the original graph is in exactly one triangle. It's kind of a subtle question here, but you can think about this tetrahedron here. If I assign this face to be a single triangle, it's actually impossible to assign the other edges to a triangle in such a way that every edge is in exactly one triangle. Whereas with the octahedron shape on the right, you can assign each face of each edge in the triangle to one individual triangle, and you're able to find this triangle partition of the graph. So I appreciate our previous talk. There's a little bit of graph theory, a little bit of a geometric thinking going on here. And so what we've done is we've actually found a way to enumerate all graphs up to 9 nodes that can be decomposed into triangles where the graphs are minimally rigid or statically determinate. So we've borrowed some work from the graph theory community, and we've developed kind of these 19 graphs here that we can decompose into triangles. And then using these graphs, we could stitch them together into larger shapes. So here's kind of a shape morphing tower here. We can imagine holding a solar panel to point the panel in different directions. Or we can imagine really bizarre shapes, like this is kind of a sort of a quadrupedal robot or something like that, that's able to change its shape through the coordinated motion of these many actuators in order to morph its shape. All right, one thing that we're excited about is that this year NASA has put out a call for developing inflated structures on the moon as part of an annual Big Idea Challenge that they do. So we have a team at BYU. We're working on adapting this type of shape morphing technology at a large scale to lunar applications. So we think we can take this robot that stores compactly, deploys to a big shape, is modular, can be reconfigured in different ways. Seems like an ideal application for lunar applications. So we're excited of exploring that application of shape morphing technology. All right, and so my conclusion today, I think that a mesh provides a really powerful framework for measuring shape change and achieving shape change. And I think us as a community can continue to think about how do we quantify and talk about shape morphing and shape change. And then I think that in shape morphing, the combination of compliance structures with shape change as a goal really enables some interesting applications. And so with that, I have a blooper reel of the robot failing, and I would also be happy to take any questions as well. Thank you.